day to you. This is Anagalactic. We are currently homing in on quantum gravity, which is, as you know, a theoretical construct. It can't be defined because it has not been discovered. What it would purport to be, if it could be discovered, would be essentially the quantum of gravity. However, if you look in Wikipedia, you'll find that there is more than one avenue of approach to this interesting proposition of seeking a quantization of gravity. So there is more than one way of conceptualizing quantum gravity. The Newtonian concept of force is what causes a divergence of opinion on what could be gravity. Newton himself considered gravity to be a force. In fact, in the standard model of particle physics, there is one undiscovered particle in their list. That is the graviton. If that could be discovered, that would be the quantum of gravity. The approach we're going to take is Newtonian in the sense that gravity must be considered to be a force. But in deference to Dr. Sabine Hossenfelder, whom I greatly respect, the logical reason for saying that gravity would not be a force is because it does not entail motion. Newtonian force has to do with motion. But gravity does not directly have anything to do with motion. As Newton would say, the velocity vector changes such that it accelerates, which Newton was well able to demonstrate. The nature of gravity is such that it should be stated a little more clearly, whether you consider it to be a force or not. If you call it a spatial force, you're being more accurate. It is a force in the sense of changing the geometry of the space. That is how Einstein essentially formulated his space-time geometry. There is a geometry to space-time. There would have to be, or there would be no application to reality. Now, in our approach, we're going to consider 8 primary forces. There are several ways of classifying and categorizing forces. To home in on quantum gravity, if we can do so, the lab cat is now approaching her perch. All right. Well, that's good luck, I think, in most civilized countries. If quantum gravity could be discovered, it would solve the quantum paradox, at least to some new threshold. Gravity is a centripetal force. Is it the only centripetal force? Gravity is a spherical force field. But when you say force in context of sphericity, it's not an outward force. That would be called centrifugal force. Can you identify a natural centrifugal force in the universe? You may or may not be able to answer that. I've never really heard anybody express light as constituting a centrifugal force, but it can be proved that that is exactly what it is. You could use the force of sunlight, and I just wanted to point out that light does have a pressure. It goes out rather than in. Those would be the 2 primary forces in spherical space at macro scale. What we're really looking for in physics, the fundamental forces that we find at micro scale. But you'll only see on the screen right now 6 forces. Electromagnetic radiation is a specific form of electromagnetism that was discovered by James Clerk Maxwell. It is also considered to be a definition of energy, which of course it is. It's not matter. There's electroforce, which is always associated with magnetoforce. They never occur alone. Even light itself is still both electric and magnetic. And these 2 are in dual, which is a very specific geometric relationship. So it's interesting that electromagnetism exhibits its force effect and magnetism, which has just baffled the mind of man forever. But you could consider electromagnetic force to be a composite of 2 forces that exhibits a 3rd force. Light exhibits centrifugal force. In the atomic force system, we of course have the electron and proton, each one of which exhibits a force of some kind. Rather than state it that way, we can look at the atom. The structure of the atom is such that we can see that there is a force relationship between the electron and proton, which is reminiscent of the relationship between electricity and magnetism, or electroforce and magnetoforce. But in the case of the atom, you would at least be able to say it's simpler. And whether there's a relationship or not, I believe we all know that there must be. But getting that relationship would be to close in on the theory of everything. The theory of everything sounds grandiose, but it's appropriate in context. It's a bit far-reaching to be a truly scientific phrase, because when you say everything, you've kind of jumped the rails. Really, the key to the whole idea, it's not a theory that we want, and it's not everything because that makes no sense. What we want is an equation of balance. Emmy Noether got a Nobel Prize for extrapolating on Newton's concept of the conservation of force, often called the conservation of energy. And of course, these are related. But she extended that to show that force balance entails a symmetry. She proved it. What I have is a theory, and I have to call it that until someone reviews it. It's interesting to ask, how is that done? Because who is going to review your work? Well, there's a system for doing that, but it's rather specific. So I accept that in good humor, but I still have my job to do. Science is really not about arguing. The cat is observing us here. There is the lab cat who really would like to participate. She's a good girl. She's basically she's going to sit on the keyboard. That's just in the atom. We can see that there's a force relationship between the electron and the proton. Now, as you know, an atom can have more than one proton, and therefore can have a whole system of electrons in shells, and that's quite significant, because that's geometric. And we will be talking about that in our journey today. The cat is just sitting, staring at me. Because she likes me. Oh, she's lifting her paw to say, "Go, Scott, go." Having a cat around is just a magnificent blessing. Beautiful creature. She knows she's going to be famous. Now, this is confessedly theoretic, but I believe that I have found something really significant at the cosmic scale having to do with force balance. In this series, we're going to be approaching the forces of the universe in terms of Noether symmetry, which is going to greatly simplify our approach. Our aim is to home in on quantum something, because we need to know what a quantum is, and there's more than one quantum.
She's staring at me. I've never seen her do this. She's making eyes at me. I just drank a lot of water, so...
Sorry. That may be a good place to... So in the next video, we're going to get very intensive. This will be intense. But my approach to science is such that I don't believe in complication. If there are complications, it means you're probably on the wrong path. What you cannot avoid is complexity. The universe obviously is complex. But is it complicated? No. Dirac didn't think it would turn out to be complicated. Einstein thought that the universe could not possibly be complicated. And many mathematicians and physicists and just scientists in general subscribe to that philosophy. And it is a philosophical approach because it's a general framework of approach, that this must be simple. And simplicity is allied with the concept of beauty, in the sense that something that looked like it was complicated, once you see the true nature of the complexity such that you can geometricize it and then prove it with mathematics. You gain simplicity, which is highly rewarding. I hope you enjoyed this thus far. In the next video, we'll be looking at this, and there are just a couple of other aids. That's the Boschkovich force curve, and that is myself giving a presentation on the mathematical underpinning of the geometry that I discovered just 3 years ago. Spherical geometry with its own number system, primarily in geometry. And that turns out to be the key to everything. So I hope you enjoyed this first presentation. My past 4 or 5 presentations have been somewhat haphazard because it took me a few days to realize how to approach this question of quantum gravity. And that's not at all what I set out to do 3 years ago or 16 years ago when I began my scientific journey. I really was into astronomy, but because astronomy involves spherical calculations, I spent most of my effort in the mathematical sense in working out spherical rotations in order to do coordinate transformations. Einstein did something similar. Einstein's field equation is extremely complicated. So's the Dirac wave equation. Thank you for your patience. We'll be back later today. And with that, I'll reach around the cat to get to the controls, and we'll be right back. Keep looking up.